Two, one, and hello, guys. And today we will be talking about second law of thermodynamics. Medyo nabitin tayo dito nung ating FICM 1 dahil na pandemic tayo. And today, itutuloy natin. Kaya nga lang ang gagawin ko is medyo pahapyaw na lang dun sa mga kailangan pa nating malamang topics and highlight ko na lang yung mga core topics dito na magagamit natin para dun sa mga official topic ng FICM 2, Chem 814. Okay, second law of thermodynamics. This is still Chem 624. Okay, we are talking about the concept of spontaneity, the Clausius Inequality, and some calculations. Mukha lang siyang broad. Mukha lang siyang konti. Pero actually, madami yan. Kaya nga lang, medyo nag-handpick ako ng mga topics na kailangan ninyo para dun sa next natin na topics. Okay. The significance of the first law. First law of thermodynamics tells us that energy cannot be created nor destroyed. Mainly in-emphasize or tinuro ko na ito nung first law natin, nung first sem. It emphasizes that the energy was conserved throughout the process. Whenever you have a process, the energy will be the same throughout. Kung titingnan natin, for example, you have a system and a surroundings, yung energy na pinopossess ng system and upon contact with the surrounding, let's say it is a closed system, yung energy nun is pag sinam mo sila, kung ano yung nawala dun sa system ay equal dun sa natanggap na surroundings. So it pretty much energy is conserved. The energy gained by the surrounding would be equal to the energy lost by the system. That's true. Assuming that the system is a closed system. Okay. The first law of thermodynamics also shows possible thermochemical process involving energy transfer. However, ito yung however. What first law can tell you is that first law of thermodynamics successfully gives us an idea on the processes of a system, but it doesn't tells us the number one, direction. So, ito yung downside ng first law. Hindi mo alam kung ano yung direction na sinasabi. Hindi ang tinutukoy dito kasi baka malito kayo is yung tinutukoy dito na direction is yung kung tutuloy ba siya or hindi or need mo ba siyang ng energy para magtuloy. So, that concept or we are also talking about the reversibility or the irreversibility of the processes. Yun. The first law doesn't define the spontaneity of the process. Yeah, talking about spontaneity. So, i-discuss muna natin what is spontaneity. Okay, let's start with the concept of spontaneity. What can you say about this video? So, ito yung isa. Ito rin yung isa. So, ayan. Kitang-kita natin na parang normal lang naman na nabasag yung glass. Nalaglag din. Nabasag. The next is ito. So, ano naman yan? So, it is a video of a glass breaking glass played backwards. So, it's like parang nabubuo siya, no? Played backwards. Excuse me. Ayan. So, ano masasabi nyo? Yung masasabi ko, yung left, it happens normally. When we saw a glass that falls down on the floor and eventually shattered into pieces. And then this one is kind of weird, no? It's kind of weird because this is not happening on the normal scenario. it's not happening on normal scenario. So, medyo weird siya. So, yan. Diba? And, yung types of processes that na ganito, hindi siya normally mo ma-encounter sa pang-araw-araw. So, ang astig pag nakakita na kayo ng ganyang bagay, wow, nabubuo yung glass on itself. The concept of spontaneity, okay, what is being spontaneous? So, spontaneous reaction proceeds and occurs naturally. If you see a process that occurs naturally, for example, you see a burning of wood, so that is a spontaneous process. Nakakita na ba kayo ng uling na biglang bumalik sa pagiging kahoy? Hindi. 'Di ba? It's weird. A non-spontaneous reaction requires energy in form of work or heat to proceed. Okay. Yung mga non-spontaneous process, these processes requires input of energy for it to occur. No? And this is some maybe evident or mainly evident on the heat engines, heat pumps, and some machines. Okay, a process that is spontaneous in one direction under a particular set, let's say chemical reaction of conditions, is non-spontaneous in the reverse direction. So let's consider here a valve containing a gas of 1 atm. So yung A is pretty much evacuated, so walang gas dyan. The B contains the gas, the chamber B, that is separated by a movable stopcock. Okay. If we consider this scenario and the scenario on the bottom, from this to this, it is spontaneous process because anong ginawa doon? So dito sarado, ang bintas dito binuksan yung valve. So it is normal to see that gases from the chamber B will diffuse to a lower concentration on A. So when gases from B diffuses to A, so the tendency is the pressure of gases or the number of gases present on B will be decreased and transferred to A. Nagets sana? Ayan. However, if we consider non-spontaneous process, so from bottom process to above process, di ba ang weird kasi the gases are actually settled na on the bottom, and imagine if we close this stopcock, ang mangyayari ba is yung mga gases from A ay lilipat uli, babalik kay B, and to form this 1 atm? No, it is not happening on real life scenario. Bakit? For it to happen, hindi ko naman sinabing imposibleng mangyari yun, but it may happen if we put energy and work in order for us to push back those gases from chamber A back to B and form a 1 atm gases back to B. Yeah. So the point here is, for a non-spontaneous process to happen, we need to put some work or energy. Okay. Another one is ice on Erlenmeyer flask. It is spontaneous when ice melts into water when the temperature is greater than 0. So this scenario shows us that the dependency or the temperature factor, how it affects the system. Okay, so it is spontaneous when the temperature is greater than 0, and it is spontaneous also when the temperature is less than 0 degrees Celsius. So mamaya makikita natin paano ba nakaka-affect yung temperature doon sa spontaneity ng reaction. Kaya nga lang, for example, you have this ice on an Erlenmeyer flask in a room. Tapos yung temperature room temp 25 degrees Celsius. It is spontaneous because the temperature is greater than 0. It is spontaneous or walang effort na need to melt the ice on the Erlenmeyer flask. You just put the Erlenmeyer flask with ice on the room and then eventually malulusaw siya to form water. Kaya nga lang, let's say nandun ka sa room pa rin and you want naman to put to make ice again from the water that is already melted. So you need to change the temperature, di ba? You need to change the temperature to less than 0. So paano mo gagawin 'yun? So you need to put you need to use something that will change the temperature of the environment to less than 0 again. So one good example dyan is yung refrigerator, di ba? Kasi ang refrigerator is a type of a heat engine that is it's like a reverse heat engine eh. So mamaya hindi ko siya i-discuss dito dahil medyo broad yung topic ng mga heat engines. So pero yun yung kanyang process. So let's consider here a closed we are still good. Let's consider here closed system together with the surrounding system. So kung naaalala niyo yung concept ng system and surrounding, so yung system is yung ating focus and yung surrounding naman is yung outside of the system. And when we take both into account, that is called a universe. So we have here a closed system, and a closed system permits the transfer of energy, right? But it never permits the transfer of particles inside this closed system to the surrounding. Okay, let's have a temperature scale here. So kung mapapansin ninyo, kulay pula yung closed system natin and yung surrounding natin ay malamig. At tingnan nyo itong atong temperature ticker. Ito yung teaser at ito yung ating thesis. This is the temperature of the system. So makikita natin mataas ang temperature ng system, tapos mababa yung temperature ng surrounding. When the closed system has had a contact with surrounding, the tendency is, syempre by the virtue of first law of thermodynamics, kapag sila ay nagka-contact at meron silang temperature difference, kung naalala niyo yung mga criteria natin kung paano magkaroon ng heat transfer, that the heat coming from the closed system will then transfer to the surrounding until they meet a certain point na kung saan yung temperature nila ay magiging equal. Di ba? Naalala nyo? Oops. O, ayan. Let's consider muna this point. Sorry. Where is that point? Ayan. Wait lang. I think baliktad yung aking I guess. Ayan. I guess tama siya. Ayun. So, the ideal case scenario, kapag at a certain point of time, naging equal yung kanilang temperature, then it is at temperature equilibrium with each other. So, magkamukha yung temperature nila. So, what if hindi muna natin sila i-take na ganun? What if all of the heat coming from the closed system was transferred to the surrounding? So, the tendency is ganito. Kung mapapansin nyo, lumamig yung closed system and then tataas yung temperature ng surrounding. But the point is, ganito dapat muna siya. Diba? dapat mag-equal muna yung thesis and teaser. And then, kapag ka ganito yung ating cycle, meaning the heat that actually the closed system transfers to the surrounding is also equal to the heat that the surrounding is transferring to the closed system. This is what I'm talking about. At this point, nasa equilibrium na yung ating system and surrounding. So, meaning, at the same time, the transfer of heat by the closed system to the surrounding is equal to the rate of transfer of heat from the surrounding to the closed system. But what if we consider this naman? No. So, balik tayo dun sa closed systems. Since mainit naman yung ating going back to this, kapag ka let's say we assume, pero this is not the ideal case scenario we assume that the heat transferred from the closed system to the surrounding is at max. So that will happen. However, guys, let's go back to this. Yan. When the heat from the closed system was transferred back to the surrounding, ito yung mangyayari. This is for irreversible process. Okay, by the way, I forgot to tell you guys that this point, at yung binibigay ko example sa inyo kanina is a reversible process. Ano yung reversible process, guys? Ganito. Ang reversible process kasi, the tendency of the reversible process is when one process happens, let's say this process, the heat transfer from the closed system to the surrounding happens, the tendency is it has also a tendency to go back to its original state. Meaning, wala kang kailangang input para bumalik yung, kunyari, yung heat na galing dun sa closed system mo ay gustong bumalik doon sa closed system. Kasi parang ang cycle, diba? The closed system transfer heat to the surrounding and then the surrounding will then transfer heat to the closed system. So, naka-design yung system na yun sa reversible process to do that kind of thing. However, with irreversible process, this happen, but in order for this to happen from surrounding to transferring from heat from the surrounding to closed system, ang tendency is ganito. So, ayan yung buong scenario. So, this is a spontaneous process. So, this process may happen in real life scenario, but in order for this to happen naman, when the heat transfer from surrounding to closed system, for example, we have a surrounding that is cold and you want to transfer the heat from that cold surrounding to the closed system, that is also possible naman. Kaya nga lang, you need to put work or energy in order for that to happen. At ganito yung nangyayari doon sa mga heat pump o sa mga heat engines natin. So parang if pag nag-research kayo, parang meron siyang hot reservoir and then cold reservoir. From hot reservoir, so doon manggagaling yung mga sources ng heat natin, and then on the system that is the heat pump, it is then processed to make work. And then, eventually, hindi naman lahat na yon ay 100% converted into work. Yung ibang portion ng heat na galing dun sa hot reservoir ay mapupunta naman dun sa cold reservoir. So, bottom line, in order for that to happen, you need to put energy or work for it to happen. Yung mga non-spontaneous na processes. So, this one is, etong scenario na to, dami-dami kasi kaninang mga close and surrounding na doble-doble yata yung copy ko. This is an example of irreversible process. So, yun. Puro highlights natin dito yung mga irreversible processes, yung mga non-spontaneous reactions. Hindi naman sila necessary o deemed necessary na impossible to happen, but it may also happen. However, you need to put work or energy. Another good example for this, for the irreversible process, is this piston. This is a piston. So, imagine ito yung pinaka-ano natin. Ito yung ating pinaka-piston. At dito meron kang, this is your piston. This is your representative atoms. And this is your movable wall. So, yung movable wall na yan, para lang yan yung kaninang stopcock na pag binuksan natin, syempre, yung mga atoms dun, pupunta dun sa walang laman. So, let's say you have a gas. Ito yung atoms niya. Okay. Pag binuksan natin, the tendency is ganito. However, ayan. So, let's say ganito. Let's try to describe na lang yung kanilang states. For example, you have your volume. Your volume is, let's say, 1 ml. Okay. Your initial volume is 1 ml. Your pressure, let's say, is 180 m. And your, ano pa ba? T. The temperature air is siguro relatively hot. So, 323 Kelvin, let's say. Okay. Pag binuksan natin yan, ganun pa ba yung kanyang states? Sa tingin nyo, hindi, di ba? Itong volume lalaki at yung pressure ay bababa. Bakit? Kasi mas magiging loose, compact na sila eh. And the temperature also will get colder. Di ba? So, let's say the volume will be twice now, 2 mils. The pressure is half of the original, so 0.5 atm. Let's say, ano lang to example. At yung temperature niya is relatively colder. So, let's say 273 na lang siya. Kelvin. So, ito yung state 1 niya. This is the state 1. Ayan yung kanyang mga variables. And ito naman yung ikalawang state. The second state is ito. So, iba na siya. From this state up to this state, it doesn't require energy for it to happen. Binuksan lang natin. Tapos, kumano na siya. Kumalat. So, it is a natural process. So, this is a spontaneous process. It doesn't require energy for it to happen. Tandaan ha, pag spontaneous process, hindi kailangan ng input ng energy. What if gusto natin siyang ibalik dun sa original niyang state? So, ano yung gagawin natin? So, this is a spontaneous process. Yan. What if gusto natin siya ibalik dun sa original niyang state? So, ang gagawin natin, pipit-pitin natin siya. So, pipit-pitin natin siya from this. So, kung sana maalala nyo yung mga state variables natin kanina. So, to this. And then again, yung ating palitan natin kulay ng pen. So, itong light. Okay, so, binalik natin siya sa state natin kanina na pinitpit natin uli siya. So, the volume is again 1 mil. The pressure is 1 atm. And the temperature is 323 Kelvin. Yeah. So, balik uli dun sa state natin kanina. So, kung mapapansin nyo, kung wala tayong ipapasok na ganito, na mechanical work, hindi mangyayari ito. Kasi parang ang mangyayari dyan is, ito, what if hindi siya gumalaw, babalik ba normally yung mga atoms na to into this point ng wala kang pinapasok na mechanical work? Hindi mangyayari yon. Kaya kailangan meron tayong ipasok na work or energy for if we want to go back to the original state, especially dun sa mga non-spontaneous process. Non-spontaneous process. At sa mga kaya need talaga natin we highlight the input of mechanical work or heat energy for this one to happen. So this is a very good example of the difference between spontaneous and non-spontaneous reactions, reversible and irreversible works. Okay, so in 19th century, Dr. Rudolf Clausius, a German physicist, coined the term entropy. So, siya yung tinerm niya na siya yung tumawag ng entropy doon. He refers to the entropy actually refers to the disorderliness or randomness regarding the atomic or particle arrangements in space. This meaning was actually adapted. This meaning was actually adapted from the Boltzmann explanation or Boltzmann distribution, Boltzmann entropy. The formula for the Boltzmann entropy is S is equal to K L and W. So yung W na to is the number of permutations or yung what do you call this? Arrangements or possible arrangements ng atom in space. Okay, so medyo malawak siya and I want to discuss kasi sa quantum. Kasi under siya ng statistical mechanics. This K, yung K na to is actually a Boltzmann constant KB. May value yung 1.6 something. Nakalimutan ko. Yung S naman is the entropy. The entropy. Kaya it refers to the disorderliness or randomness because the perspective here is the molecular arrangement or states. So, meron tayong mga tinatawag na mga microstates. Kung gaano kadami microstates na yun, it represents the double. It is represented by the value of W. Okay. Erase ko muna. The entropy is a state function, delta S. So, delta S is equal to S final minus S initial. So, if this is a state function, we measure the final value minus the initial value. The formula for the S is dQ. Okay, this Q is the heat involved. Familiar siya sa inyo, ano? Kasi na-encounter na natin siya sa first law of thermodynamics. So, sa heat involved. And this T is actually the temperature. This one is in Kelvin, this one is in joules. So, ang unit ng entropy is joule per Kelvin. Okay. For isothermal this is on isothermal processes. Next. Let me check kung good pa tayo. Okay, we're still good. Okay. For the Clausius inequality. The Clausius inequality or the Clausius theorem is a mathematical explanation of the second law of thermodynamics. It was developed by Rudolf Clausius, who intended to explain the relationship between heat flow and the entropy of the system and its surroundings. Bakit ba natin pinag-aaralan yung entropy in the first place? Kasi nabanggit natin kanina na yung the first law of thermodynamics actually fails to give the directionality of the certain processes. So another scientist or another physicist actually makes a term that the goal is to have a criterion to make a criterion for us to determine the direction of the processes. So it also gave us an idea kung yung process pa na yun is magtutuloy ba or may happen in real life or not. Okay. Let's try to consider this by pondering on this image. This is from I forgot kung saan galing to, Ohio University. So, this is the heat source. So, meron tayong dalawang heat engine dito. So, this is a system of the heat engine. Again, ang heat engine kasi is it converts heat into work. So yan ang pinaka natin, yun ang pinaka goal ng heat engine. So meron tayo ditong reversible heat engine and irreversible heat engine. So in a reversible heat engine, kung makikita natin, ano yung unang-una nating makikita? In reversible, mas malaki yung work na nagagawa niya, meaning the efficiency of the reversible heat engine is larger. Okay, so efficient siya. However, paano natin siya nasabing efficient? Diba ang goal nga ng heat engine is to convert heat energy into work. Since malaki yung work niya, so it is efficient yung system na yon. At kung mapapansin natin, hindi nga lang siya 100% na nakakonvert into work dahil yung ibang heat ay natatransfer doon sa ating cold reservoir na papunta dito sa baba. Okay, so there is a theorem that actually says that there is no 100% efficient conversion of energy, and that is the Carnot theorem. Kaya meron ditong Carnot. Hindi ko siya napiling i-discuss, sorry. Okay. So let's try to saan na ba ako? So let's try to ponder on this. Ito naman, on the irreversible one, we can see that we pretty much start with the same amount of heat. See? It is equal. Actually, we take that as an equal. Kaya nga lang, kung mapapansin nyo, yung irreversible work na nagawa ng irreversible engine natin ay mas maliit kumpara doon sa ginawa nung ating reversible heat engine. So, this is less efficient, this is more efficient. At kung mapapansin ninyo, mas marami siyang ibinagsak na heat doon sa ating cold reservoir. So, ano yung implication na to? So, mapapansin natin na yung reversible heat engine ay actually efficient compared dun sa irreversible processes. So, this we take this as a reversible processes, and this one we take this as a irreversible process. Okay, paano ko nga ba din i-describe to? Kasi 'di ba pinag-aralan din natin nung first sem, nung Chem 624, 'di ba? On an ideal gas processes na lang. Consider natin ideal gas processes. In an ideal gas processes, the heat is conserved throughout the system. Let's say you have a canister that is filled. We have a canister that is actually filled with so much gases. We assume if that is an ideal system, we assume that yung mga energy doon is conserved kasi in a real life scenario, kapag ka naglagay ka ng gas dyan sa isang canister, those gases is continuously hitting the walls. Tapos syempre magbabanggaan pa sila ng gas to gas. So meron tayong mga elastic and inelastic forces doon. So ang tendency is yung mga energies doon is not conserved in real scenario. Pero in ideal scenario or for reversible processes, ayun. So halos parang walang nalolos na energy. The energy lost in reversible processes is very minimal. Yun. Which is also an evidence kasi kung bakit, kung mapapansin nyo, yung mga heat na napunta doon sa heatsink ay mas mababa compared doon sa heatsink na napunta doon sa irreversible processes. Kaya mas efficient yung reversible processes. Okay, we're still good. Okay, considering the ideal heat engine, so ito yung final equation natin. So, titingnan natin kung paano tayo nag-arrive sa ganyang equation. So, let's take the ideal gas process. The reversible heat engine. Okay. This is the Clausius Inequality. At first, by describing the the entropy of the ideal heat engine. So we take the differential, the dQH, or the differential of the heat that is actually the heat that comes in dun sa ating heat engine with respect to the temperature H of the hot reservoir, minus the dQL rev divided by TL. This dQL is actually the residual heat that is not converted into the work. So yun. Tapos divided by the temperature of the cold reservoir. By the way guys, take note. This Clausius inequality is actually the sum. Meaning it is the sum of all the entropy that comes in and comes out of the system. Kung mapapansin nyo, this dQH over TH was actually coming in the system. The system we are talking about is the heat engine. And then kung mapapansin natin, our work is actually done by the system. So when work is done by the system, meaning that is a negative work, kaya nga lang inumit natin since we are talking about the entropy here. So we are only concerned with the heat muna. So another one is the Q is coming out the system. So this is dQL rev divided by TL. So this is the entropy that is coming out of the system or the reversible heat engine. And take note, that is equal to 0. So for reversible processes, the Clausius theorem, or the total entropy of the system is equal to 0. Tandaan, laging equal to 0. This is true with cyclic reversible systems such as the heat engine. In a heat engine kasi, hindi lang siya one-way ticket, parang nagsa-cycle siya sa loob. Okay, so next one is yung kanan part naman is yung this is cyclic irreversible systems naman. So yung heat engine, kung mapapansin natin, the same value lang naman yung dQH niya. However, ang laki nung hindi na-convert into work. So this is a less efficient heat engine. So how can we go with that? So how can we describe this in terms of the entropy? So let's try to know kung ilan yung entropy na pumasok sa system. So the same, dQH divided by the temperature of the hot reservoir here, minus, so we are referring to the entropy that is coming out the system. So how can we know that entropy? So kailangan natin munang tingnan yung difference nung ating entropy that comes out on a reversible process and the entropy that comes out on an irreversible process and take their differences. That's why meron tayong ganito, dQ divided by T. This dQ is actually the difference of this heat that comes out from reversible and irreversible process. That is plus, the difference is plus because common sense, mas malaki yung QL natin here kumpara dito sa reversible. So meaning, ipa-plus natin yun kasi yung difference niya is mas malaki yung nandun sa irreversible. Kaya nagkakaroon tayo ng inequality. This inequality here is the Clausius inequality. Kaya less than or equal to 0. So, ayun. Dun siya nanggaling. Diba? Galing. So, from this equation, dito na nagkaroon, this equation was actually it is rigorously derived from the Kevin Planck statement. Kaya nga lang ayoko sanang ipaano muna sa inyo yung Kevin Planck statement that is on heat engines. Kaya nga lang, this one is very crucial for you. This is a very crucial equation. The second law of thermodynamics, in an ideal universe, ito, medyo gaan na natin yung topic natin. In an ideal universe or reversible process, we take the entropy of that universe equal to the entropy of the system, and the entropy of the surrounding equals 0. Okay? That is for reversible or internally reversible processes, yung ibang term. So, meron akong binigay dito kung paano yun na-derive. And this one, yung real universe naman, in a real scenario, irreversible processes, that delta SU is actually greater than 0. This equation came from the Clausius theorem, which is derived from here. You can check na lang kung paano siya dinerive if you want to know. Ito yung one. So, Ohio University siya galing na material. The delta SU is equal to the delta SCs plus delta S surrounding. So, yung mga inequalities na yan, depending on the type of processes you have, whether it is reversible or irreversible, so, dun nag-root out yun dun sa Clausius Inequality. Kaya dapat talaga malaman natin. Okay, let's talk about the third law of thermodynamics. So, tandaan niyo yung dalawang formula na yun, yung delta S universe. Magagamit natin yun mamaya. Since entropy is a state function, we can also treat it similar to enthalpy. We can also perform computations like the Hess law, but using standard molar entropy. If you recall Hess law, the Hess law is actually came from the first law of thermodynamics, di ba? The first law of thermodynamics states that the energy of the system is conserved throughout, meaning the energy of the product, the summation of the energy of the product minus the summation of the energy of reactants, yun yung pinaka enthalpy niya, standard enthalpy of the reaction. So that's like. Kaya nga lang, in this entropy can be also be treated like that since it is a state function. Similar to the Hess law, pwede natin computein din yung sa entropy. Nakahawig nung pag-compute natin dun sa enthalpy of the reaction. So, katulad ng enthalpy of the reaction, meron din tayong tinatawag na entropy of the reaction. At bawat atoms, katulad nung sa enthalpy, ay meron din silang tinatawag na S naught o yung standard molar entropy. Okay? The tendency here is the larger the molecule, the larger entropy it has. The larger and the more modes of molecular motion it can do, the greater the SME, which correlates to the bulkiness of the structure of the atoms or the compounds. So, mayroon kayong SME, yung standard molar entropy. Attach ko na lang sa Google Classroom after ko ma-upload ng video nito. Entropy in chemical reaction. So, familiar na kayo sa enthalpy, pwede nyo rin gawin yun sa entropy. Okay, same lang din. I-multiply nyo lang, isasum nyo lang lahat ng molar entropy nung inyong mga species sa products at molar entropy. Siyempre, i-multiply nyo din ng ng coefficients. Kaya nga lang, unlike enthalpy, pag meron kayong pure elements like H2O2, Cl2, Br, F, N2, puro sila zero. Or katulad ng mga pure element, katulad ng Fe solid. Yung Fe solid, ano pa ba? Mga example, Na solid, ganun. Zero lahat yun pagka sa enthalpy. Pero hindi sila zero sa entropy. Bakit? Kasi, yung phase ng matter, nagmamatter, ay parang awkward. Yung phase ng matter is actually nagmamatter din doon sa entropy. Whether it is a solid, yung solid kasi mas compact yung kanyang system, and remember that entropy can also be reinstated by molecular arrangements, di ba? Just like the ina-mention ko kanina yung sa Boltzmann entropy. So the tendency is mas mababa yung entropy ng solid dahil mas compact, mas konti ang moments o yung mga microstates na pwedeng mangyari. Unlike dun sa liquid, yung liquid medyo loose, medyo mataas ang entropy niya, and yung gas. Okay? Yung gas na yon, whether it is an H2, an O2, a Cl2, mataas, meron niya ng entropy. Or kahit pa yan ay Fe solid, yung Fe solid siya o N2 solid siya, Na solid siya, meron niyang entropy. So it's not equal to zero. Tandaan niyo yun. Calculate the change in entropy associated with the Haber process of the production of ammonia. So galing to ng Chem Libre text. Sagutan natin to after ko ma-upload. After nyo mapanood to. Okay. Bali, PM nyo ako guys. PM nyo ako kung tapos nyo ng panoorin, and then i-upload ko yung sagot kung tama kayo. And kung masasagot nyo ng tama, then okay, may grades. Next is entropy in chemical reactions. We mentioned earlier that the main use of second law of thermodynamics is to predict the directionality of chemical reactions. Okay, so na-mention natin yun kanina. What is this direction? Consider a reversible isobaric system where dq is equal to dh in a universe. So, this is the formula yung mini-mention ko kanina. Dapat ako tandaan ninyo. And also, yung value ng delta S is also equal to the delta Q. Yun yung kaninang, nung in-introduce ko sa inyo yung word na entropy. Ito yung formula niya. Delta Q divided by T. That is true for entropy. And then, applying this equality here, the dq is equivalent to the enthalpy of the system. Okay, entropy in chemical reactions. Then solving for the delta S, continuation nung kanina. This is the delta S of the surrounding. So, we consider this as negative H. Wait, this is wrong. Mali ito. Let me correct this one. This one should be system. Bakit? This one should be system. Are we good? Oh, we're still good. This one is system. Papaliwanag ko kung bakit. Bakit we are using a variable that represents the system? Let's say you have a system and then you have a surrounding, diba? Kapag this one is a closed system, so ang tendency is it will transfer energy. Let's say higher energy yung nandito sa system natin. It will transfer energy from the system to the surrounding, diba? What if we want to account for the entropy of the surrounding that actually receives that energy? Ganito pala siya. Whether we want to if we want to describe the surroundings, diba? If we want to describe the surrounding, kasi ang tendency is when this happens, the energy that comes from the system will be transferred to the surroundings. So meaning the Q here is negative. So if this is the scenario, transfer from the system to the surrounding, and then the Q here is positive. Okay? But when we have a spontaneous process, this one, the S of this is, hindi siya kitang kita. Let me erase muna. The tendency is ganito, negative delta Q surroundings. What if we want to express the surrounding? Kasi hindi naman natin directly ma-measure yung mga parameters ng surrounding kasi in the first place, yung system ang ating pinag-aaralan, di ba? So what is the deal with this? We use the parameter of the system and the application of first law of thermodynamics na ang ibig sabihin niya ay lahat ng heat na inilalabas ng surrounding o na inilalabas ng system o tinatanggap ng system ay equal din dun sa heat na galing sa surroundings, 'di ba? So in this point, if we want to emphasize the surrounding in terms of the system, so we use a negative delta H of the system that corresponds to the direction of the heat that it came from. So this came from the system. If we are referring to the delta S of the system, this is positive. Kaya nga lang we are referring to the delta S of the surrounding. So this one should be the opposite sign. Okay. Applying it to the formula, so balik tayo dun sa formula kanina. So ito yung original formula natin. So we are actually describing. So this H sur is ito na siya. Delta H not S is. So take note, if we are actually referring to the entropy of the universe, hindi na natin kailangan pang directly i-measure yung delta S na surrounding. Tingin na lang tayo dun sa system. Okay? So entropy of the system, magagamit natin siya. At yung heat also ng system, kaya nga lang negative value, magagamit din natin siya to compute for delta S of the universe. Entropy in chemical reactions, again. So, eto, from this, ang ginawa natin, para ma-standardize natin, we multiply, we multiplied both sides of the equation since the temperature for the system and the surrounding is only the one. Isa lang na may kino-consider natin. This let's consider this an isothermal process. Okay. So the temperature we are referring to is actually the same. So we multiply that by T, cancel. So ang mangyayari is ito magiging T delta S at ito ay magiging T delta S, diba? Ganun mangyayari. So ang mangyayari ayan, T delta S of the universe is equal to T delta S of the system plus negative H not cis. Kaya nga lang nag-derive tayo kung paano natin makukuha yung value na to kasi this one has meron siya equivalent value. Kaya nga lang yung negative sign niya. Meron siyang corresponding value and that is G. Ano tong delta G? That is, ang tawag dyan ay Gibbs free energy. Okay. Ito yung na-derive natin kanina. So, may papakita ko sa inyong video dito. So, ipa-fast forward ko na sobrang bilis para makita nyo kung paano tayo nag-arrive dun sa ganun. Pwede nyo i-post yan. Okay. So, actually, this is the value of delta G. But, if dun sa original equation na na-derive natin, bakit parang hindi yata tugma? Kasi magkaiba yung sign. This term is negative. Positive. This term is negative. Madali lang. itong T delta S na to, i-multiply nyo negative 1, lahat na yan magbabago ng sign. So ang ibig sabihin, yung delta G is equal to negative T delta S of the universe. Nagets nyo? So ulit, itong delta G ay equal doon sa dito negative T delta S of the universe, which is equal to H naught cis minus T delta S. So dito nanggaling yung formula ng Gibbs free energy. Ito yung pinaka-formula ng Gibbs free energy. So, yung delta G, that's the Gibbs free energy. Yung H cis is the enthalpy of the system minus the temperature, and the delta S of the system. We can actually get this. We can measure this, and this one we can also measure this. This is called the Gibbs free energy. Clear ko lang lahat ng Gibbs free energy. Okay, a Gibbs free energy is a thermodynamic potential of a chemical system that involves energy associated with the maximum work the system can be done. Okay, so paliwanag natin, no? We also use this Gibbs free energy kasi to determine the spontaneity of the reaction. So kahit anong type pa ng reaction niya, whether it's an electrochemical reaction, I don't know nga lang pala kung nuclear reaction is counted. Chemical reaction, hindi nuclear. So, yung chemical reaction. So, electrochemical measurements, ano pa ba? Reaction of gases. You can also use that on the reaction of gases and standard chemical reaction, aqueous reactions, and also the thermodynamic equivalent of this. Yung Gibbs free energy, sobrang dami niyang gamit. Kasi the Gibbs free energy is actually one of the fundamental thermodynamic formulas, thermodynamic functions. So, kung hindi ko lang naituro sa inyo kung paano mag-compute using a Batov sheet, pero maraming use ang Gibbs free energy. It actually refers to, kaya nga parang Gibbs free energy, it is the associated with the available energy for the system to make work. It is associated with the maximum work the system can be done. As equilibrium criterion also in chemical reactions and correlates putol. It also in equilibrium criterion in chemical reaction, it correlates the the activity or what do you call, ang tawag dun sa equilibrium constants. Okay, it actually correlates the equilibrium constant with the Gibbs free energy kasi ang derivation niyan is negative RT ln K EQ. Oh, yun, tama. Equilibrium constant. Tama. In electrochemistry, we utilize also the Gibbs free energy in determining the reduction potential. So, we use Gibbs free energy to determine the standard reduction SRP, standard reduction potential, o yung ENAT, reduction potential. So, yun. Konting trivia kasi we use Gibbs free energy with paano ba ginagamit yun? Delta G is equal to negative NFE. Delta G is equal to negative NFE. So, from that equation, i-derive natin kasi yan in order for us to relate the Q on the K. We are actually parang pinag-merge natin yung chemical equilibrium with the electrochemical one. So, from that, yung merge nila, pwede kayong makagawa ng formula. Actually, yun yung Nernst equation to relate the K and the E or the reduction potential. So this is the interplay between them. So makikita natin here. So meron tayong from the calorimetric measurements, the Agatas form, delta G is equal to delta H minus T delta S, we can actually correlate that with delta G is equal to NFE for the electrochemical applications. Ito yung sinasabi ko kanina, which is the E, o yung standard reduction potential, so reduction potential nung system natin. And we can also correlate that with the K equilibrium constant. Tama ba? Sorry, weakness ko po yung analytical chemistry. It's at equilibrium constant. We can also correlate that both. And this equilibrium constant, we can also correlate that with the calorimetric or the thermodynamic measurements by using the RT, L, and K, which is very, very useful in determining the spontaneity of the given reaction. That is actually applied on thermochemistry. Chemical reactions and conditions. If delta G is negative, the forward reaction is spontaneous. Kapag yung value niya is negative overall, it is a spontaneous process. Look at this figure on the right. The extent of the reaction here is it's fast. Ang bilis niyang mangyari. And the delta G here is actually high, but is less than 0. Okay. Next is the delta G here is equal to 0. So at this point, they are at equilibrium. Okay. Na-discuss na yata natin to last time. Ang concept ng equilibrium is when the forward reaction, the rate of forward, hindi pa. Di-discuss pa lang pala natin to, guys. Sorry. Bigyan ko na kayo ng spoiler, no? The equilibrium state is actually, we are talking about here the rates of the reaction. Kapag ang forward reaction mo ay equal sa rate ng reverse reaction mo, then the equilibrium is achieved. When the delta G is greater than 0, that means positive. It is non-spontaneous process. Kaya nga lang, considering that you have a two-way process, if you have a two-way process, then the reverse reaction is actually spontaneous. Okay. There are two parts of the free energy equation. So, if we look at this one, this is the first part and this is the second part. On the first part, we have a term here, the enthalpy, and we have a two term here, this is that entropy term multiplied by the temperature. So, para malaman natin kung ano ba yung conditions natin, kung spontaneous ba siya, non-spontaneous ba siya, magdedepende yun sa value ng H, sa value ng T, at sa value ng S. But however, ganito, itong second term, the entropy term, tinitake natin siya as isa, yung temperature, kasi tinitake natin siya as kasama ng S. Depende pa yan sa sign ng delta S. Okay. So, yung temperature kasi, wala naman negative Kelvin temperature. Ang negative temperature. Kasi, according also to, di ba, it is almost impossible for us to attain the absolute zero temperature. Negative Kelvin, the less beyond absolute zero pa yun. So, ayun, it's rather impossible to happen. So let's check if we're still good. Yes, we're still good. This equation satisfies the isobaric and isothermal systems, no? If this delta H is actually positive and this delta S is, if this delta H is negative and this delta S is positive, yes, So, if this is negative and this is positive, so this term, ang mangyayari ay negative siya. So, kung ganon, kung negative ito at negative din ito, depende nga, hindi, negative 2 eh. So, kahit anong temperature pa yan, spontaneous yung delta G dahil ang mangyayari, negative siya. So, ayun, tama. Spontaneous at all temperatures. Next is, pag positive yung H-sys mo, so, at negative naman itong T delta S mo, so, kahit anong temperature na to, so, negative times negative, hindi magiging positive tong term na to. Ito naman, positive. So, magpa-plus yan. So, matic, positive yung delta G mo. So, non-spontaneous kahit ano pa yung value ng T. Okay. Next is, kapag ito ay negative at negative din daw, yung iyong delta S, so that is minus, ito magiging plus. Nako. Meron ditong point na magiging spontaneous o positive yung G o negative yung G. Kapag yung temperature ay siguro, magiging positive kasi ito eh. Pag yung temperature may ubod ng taas, magiging positive yung G. Pagka doon sa ganitong scenario pag negative to, negative yung delta S mo, di ba negative, magiging positive to. So, kapag sobrang taas ng temperature mo, ang tendency is this term will be positive, super positive, ma-out positive niya yung ma-out value niya yung H-sys. So meaning, ang magiging sagot dito is positive delta G, so this is a non-spontaneous at very high temperature, kaya ganun yung kanyang explanation. However, kung mababa yung temperature niya, so mas mataas yung value ng H-sys kumpara dun sa value na to. So, mas mataas yung negative value compared dito sa positive value. So, this one will become negative and spontaneous at low temp. Next. If the H-sys is actually positive, and this one is also positive, so this value becomes negative. Okay, ito positive. Pag ito ay mataas, meaning at higher super high temperatures, ma-out negative niya yung value ng H-sys. So, meaning, at very high temp, spontaneous siya. Tama ba? Okay, tama. Kapag ito ay positive at ito ay positive din, so magiging negative tong term na to. Kapag ito ay mababa ang temperature, so ma-out positive naman ng H-sys yung term na to. So magiging positive yung delta G. So at mas mababang temperature, sila ay non-spontaneous. Tama. Ganon siya ini-interpret. Depende siya sa value ng mga variables mo, H, T, at delta S. Tapos depende sa sign. Kaya dapat medyo maging meticuloso kayo doon. Yan. Try nyo sagutan to. 1, 2, 3, 4, 5. Ito pa. Post nyo na lang. Ito, maganda tong tanong na to. Kinopya ko lahat naman din sa ChemLibreText. Tapos, ayan. Ito, hindi ko na alam kung saan ko pinuha to. Download kayo ng standard molar entropy, SME. So, yun lang, and I hope marami kayong nalaman ngayon sa ating lecture na medyo mabilis lang siya. Pero pretty much na-cover natin yung mga kailangan yung malaman. So, yun lang, and thank you, and stay safe.